You are welcome to start now.
Cool. Let me share my screen. Great. Can everyone see my screen fine?
Yes, we can see.
Perfect. Okay. And you can hear me fine?
We can hear you fine. Maybe I'll just mention there, as there's a lot of people on the webinar, you can raise your hand if there's any questions, but I think we'll try and go through the whole webinar series and then finish off at the end, and then John and I will give some time for questions. So you're welcome to put your question in the chat, and then at the end we'll answer all the questions. Okay?
Oh, cool. Thank you, Laura.
Thanks, John.
Awesome. Okay, thanks, Laura, for the introduction. So I would also just like to welcome everyone to this Ansys FEA Webinar Series. And yeah, thank you for taking the time to join us today. So as Laura mentioned, my name is Jean-Marie, and I work for CubeSoft as a mechanical FEA engineer. And I'm also accompanied on this meeting by my colleague, Jessie Quick, who will be available for questions in the chats and afterwards, of course, as well. Okay, so to get started, so as you know, this webinar series falls over 3 Fridays, this being the first session. And the aim of this series is to demonstrate the typical process of conducting a static structural analysis. And this process will be broken up into 3 sessions, with today the focus being on SpaceClaim. So we'll be focusing on preparing and optimizing the geometry for simulation in SpaceClaim, and the following sessions will be more focused on the actual simulation itself and how to get the desired results and so forth. Okay. The duration states as 90 minutes, but I suspect we'll probably be busy for about 60 minutes maximum. So, but let's see how it goes. Okay, so to get started, the geometry we have selected for this webinar series may surprise you, as it is simply an office chair. But we decided to go in a bit of a different direction, just in order to show you just how versatile the software is in analyzing almost anything that you desire. And we will typically be applying the same fundamental, how can you say, principles in any case, and we'll be using the same tools to do so. So I'd just like to mention, so when we do our static structural analysis, as with other types of finite element analysis, you get your geometry that you import, you then prepare and optimize it in a tool like SpaceClaim to make it ready for simulation. Then of course you'll do your meshing and apply your boundary conditions, etc. So why do we clean up our geometry? So in many cases, the imported geometry is not quite ready for meshing. This could be due to a variety of things, such as like broken surfaces or surfaces that are not properly stitched together, things like multiple edges or duplicate surfaces, and then things like surfaces that are way too small to be meshed reasonably later on. So these things you kind of want to eliminate, just to make your analysis later on more efficient and more streamlined. So this is why we do it, and it's also quite beneficial to reduce the complexity of your model as much as possible, of course, without compromising the quality or rather the accuracy of the geometry. So this is the reason why we do this, and I've also found that the more time I actually spend on preparing my geometry, the less time I spend on troubleshooting in mechanical, and I have less like meshing issues, and it's just a lot easier to scope things. So yeah, so today we'll be focused on that. So as you all know, Ansys SpaceClaim is an industry-leading direct modeling tool, and it's got built-in features that is analysis focused. So these tools are specifically included to help you prepare your geometry for simulation. And then today I'll be showing you some of these tools, applying it to our office chairs. So yeah, Jesse and I we just decided that we've seen that there's analysis done on pumps and tanks and structures, and today, you know what, we just wanted to see what is the structural integrity of our office chairs. So we'll be focusing on some of the design and repair tools today, and we'll also show you how to optimize geometry by creating some midsurfaces and extracting beam elements. So this is essentially when you just convert your like a 3D solid to a shell body, or you can even convert like a beam-like structure to a 1D element. So this is just to obviously optimize your mesh and reduce your computational time. Okay, so to get started, let's just jump straight into it. I'm just going to open SpaceClaim. Okay, so for those of you who are not familiar with SpaceClaim, this is what the interface looks like. It's quite similar to your other CAD packages with your GUI interface. You have your structure tree. In the structure tree, you will see all your components, be it a solid or a surface or a geometry constraint or anything like that. You'll see it listed in there. And at the top here, you have your ribbons with all the tools that you can actually use. So you have tools here to do modeling. You have the sketch tab to do your sketching, your design tab to predominantly manipulate some of the geometry, and then some other features that you can use like assembly and sheet metal. But mainly today we'll be focusing more on some of the design tools and some of the tools that we use typically to prepare our geometry for FEA. So I won't be covering all of them specifically for time mainly, but I think I'll be covering most of the ones that I use the most or have been using the most. So I hope you can take some value out of today's session. Okay, so I'm going to open my geometry now. Just want to make sure I select the correct one. Okay, so in SpaceClaim, you can import a variety of different files. I forgot to show that now, but there's a variety of different CAD file types that you can import from other CAD packages. So in this case, I already had a SpaceClaim file. So the reason being is I have done some minor geometry cleanup in terms of just kind of grouping the parts together and making sense of the assembly. So in this case, as you can see, I've grouped the geometry in a few different sub-assemblies. This is actually quite easy to do. So this is usually my first step, is I go through the components and I organize everything that it makes sense structurally so that when I am in mechanical, you know, it's easy to scope things and suppress things and hide things. So it's quite useful. And just to show you, it's quite easy to manipulate this. If I just want to move, you know, this end cap to be in the sub-assembly, I can just drag and drop it. And you'll see that it's over there. I don't want to do that now though. Or you can select some components. Let's select, I don't know, these two, and you can move that to a new component as well. So you can manipulate your sub-assemblies in this tree, but I've already done so just to save time for today's webinar series. So, okay, so here we have our geometry. Some very basic office chair, as you can see. But yes, let's see what we can do to this office chair to make it ready for simulation and have it as efficient as possible. Okay, so the first thing that I usually do after, you know, organizing my structure tree is to kind of identify which components I want to suppress for physics. So these are typically components that I don't see are very necessary for load transfer, or they're more like an accessory or aesthetic or whatever. So in that case, you will suppress those components. In other cases, it's also possible to suppress components that you feel is not relevant to your study. So that's all good. I think it's always useful to make your model as small and efficient as possible. So selecting your boundary, I don't want to say boundary conditions, but like your battery limit of your model is up to you, and that is up to your engineering judgment. So in this case, let me show you what I've decided. I've decided that I'm not really too interested in the wheels and the wheel supports. I'm more really interested in this bottom structure of the office chair. So typically we'll have our static load due to the weight of the human, and we will later on apply some maybe some gravitational loads and acceleration loads and all sorts of things. We'll see. But for now, all you need to know is we need to optimize this for static structural. Okay, so to suppress the components that I want to, I have already grouped them. So I simply just right click on this and select suppress for physics. So the wheels are suppressed. Not the wheels, the end caps, sorry. But similarly for the wheels, I also want to suppress them. So I'm just suppressing these end caps. They're not really significant to me. And also the wheel and all of these support components. So then the other thing I want to suppress is this lever over here. I will probably represent it by a joint or something similar like that. So when you do suppress a component, it's necessary to represent it by applying the correct boundary conditions or joint or whatever. So I think in this case, it'll probably be a joint, but I'm going to suppress. Then when you're done with that, I usually just hit hide all suppressed and I can see what I'm left with. Okay. So now, usually what I'd like to do is see which components would be suitable to Midsurface, or in other words, to convert to shell bodies, which ones would be best as a 3D solid, and then which ones could be beams. So in this case, I thought the cushions or the support of the office chair would probably be best as a solid, and most of these supporting plate-like structures are probably Midsurface, and then the feet support, I'll call them beams because they are beams, I will represent as beam elements. So in that case, it would be the most efficient, and it would still represent the geometry as you generate the mesh. Okay, so after this, I'm going to start with the 3D geometry perhaps. So before I get into that, I'd just like to point out that there are a variety of automatic tools within SpaceClaim. So they're mostly captured underneath the repair and prepare tab. So some of these tools, when you click on them, like simplify, will highlight a variety of edges and usually like spline faces and things that it could simplify. But it's important to note that it's not necessarily an indication of whether the geometry will mesh. So sometimes you can get a lot of edges that SpaceClaim says needs to be simplified, but that doesn't mean if you don't simplify it, it won't mesh. So most of the time, I'll just kind of simplify and reduce the complexity as much as possible, and then try and mesh it. And if there are any additional problems, then I'll go further and investigate why a certain component is not meshing, or why, you know, there's not shared topology or something like that. So in this case, I'm going to just demonstrate one of these tools. I'm going to look for small faces. As I mentioned previously, we don't like having small faces because if you need to represent that in a mesh, you'll need tiny elements to represent that small face, which is not really necessary because it's joined to other faces in any case. So I'm just going to try find, let's say, everything below 0.2 millimeters. Okay, so it's found 3 areas. As you can see, there are tiny, tiny, tiny faces over here. So you can just click on it to remove it, or you can hit the check mark for SpaceClaim to fix all the problem areas. So that's just an example of how you can use some of these automatic tools to kind of get rid of most of the issues, but there will always be some things that you still manually need to fix. Okay, the next thing I'd like to show is just, for example, on this cushion over here, there's lots of different faces here that would probably be better either merged, or you could apply a name selection to them as well to group them together. So I just want to demonstrate how you can just merge the faces. It's quite simple. It will be under the repair tab. So this one takes a bit of time. That's why I won't be merging all of these faces. But as I said, it's not necessarily a like mandatory requirements. It's just something that makes your model more efficient. So as you can see here, it merged those faces together. Then if you decide there are some weird looking faces like these two on here, you can just kind of remove them again to just kind of reduce the complexity. So those faces over there. Okay, that's not too bad. I think I'll remove this sliver as well, perhaps. Okay, so I'm not going to remove all of these faces now. It will still be able to mesh. It's just to show you what you can typically do to make it a bit more efficient. Let me focus on these armchairs now. So these are also going to be solids. I think I'll also just remove some of these small faces over here so that the mesh does not have to capture this detail, because it's not really necessary for the structural integrity of the chair. I'm going to remove the bottom side as well. Okay, and the other side. Okay, cool. That seems fine. There's some other components that will also be 3D, probably this one. So I'm going to use the fill tool to remove these chamfers over here. So I also don't want to capture this detail by the mesh. So simply just select all of these faces and remove them. Okay. You can see it's tiny little details that we change, but in the end, it makes a massive difference to the time you spend in mechanical trying to fix things. Okay, cool. There we go. I think our solids are fine. The main thing I actually really wanted to focus on today was the mid surfaces. Just see there is a question or something. Okay, no, sorry, they was flashing on my Teams. Anyway, okay, so yes, as I said, I would like to focus on the mid surfaces today. So luckily over here, there are quite a few components, as you can see, that could be represented by shell bodies adequately. So if you had to mesh this body, for instance, with solid elements, it's best practice to ensure that there are 3 elements across the thickness. So that's best practice for finite element analysis. But sorry, I just saw the question now. So that's why it's always best practice to rather use shell bodies, because you can represent the same kind of detail. And mechanical does provide you with the tools to, if you need to extract the through thickness stresses or things like that, you can actually do that as well. I'm also going to show you when you do the mid-surfacing that the thickness of the surface is automatically also extracted. Okay, so let me start by just adding some of my solid bodies to make it a bit easier. I'm gonna hide these as well. Okay, cool. Let me start with my mid-surfacing. So before I start, as you can see, there are some rounds on this body over here. This is not a problem. You can still probably mid-surface this body, as I will show you now. So I'm going to use a range to do this mid-surface. You can select faces. So this is one of the options that you can do to create a mid-surface like that. But I prefer to use a range to mid-surface a whole body. So in this case, I'm just going to use 0.5 millimeters. So then it will mid-surface everything within that range in a body. So if I select this and I mid-surface it, you will see if I keep the rounds in, it still captures the curvature over there, which is not really something I want when I want to mesh my geometry. So I'm just going to undo that and first maybe remove the rounds. So to do that, I think it would be best to use some of my power selection tools. So I'm going to select this round. I want to actually remove all the rounds on these bodies over here. And to do that, I'm just going to go to selection and say search all bodies, that's usually visible, and select the rounds that are equal to 2 moles. Okay, so you can see all of them are highlighted now, and that is great. So now I can just go to prepare, hit the remove rounds tool and the check mark, and all of these rounds, which is quite nice. So I think that is it that I need to simplify for the mid surfaces. There are also rounds on these beam bodies that you can see, but I will actually be extracting that whole cross section when I extract the beams, which I will show you a bit later. So, okay, I'm going to start with my mid surfacing. It's under the prepare tab. So again, I'm going to use the range. It's just a lot faster to mid surface. So when I click a body, you can see it highlights the body with like a green and a blue face. It just kind of indicates the orientation of the top and the bottom of the shell, which you sometimes need to define in mechanical, like which orientation of the shell is in contact with another one. Okay, so I'm just going to start by mid-surfacing that. And you'll see as I mid-surface a body, it automatically suppresses the 3D component that it just converted. So you don't have to go do that manually. So I'm just going to mid-surface all of these quickly. This is actually a hollow part, as you can see. So it'll be mid-surfaced as well. Okay, cool. This one is a bit thicker, so I'll probably use, I think 10 mils should do it. Yes, okay, so that's fine. So even if it's quite a thick plate or beam or anything, it's still fine to represent it as a shell body. Okay, so those are all fine. I'm going to start mid-surfacing these plates as well. Let's see how they do. I'm just going to change that 5. Okay, so it's identifying all the faces properly. Let's see. Okay, cool. That seems fine. And that one is quite simple. Great. This one is a bit interesting, but it still captures it adequately. Okay. I'll probably get back to extending some surfaces now just to kind of share the topology, but we'll get to that. Mid-surface this pipe, and then this is also a surface-like component. So let's see, let me use 5 mils. Cool. Okay. Now you can see the see-through version. Okay, cool. All the mid surfaces that I have in my model now, they are all represented in the structure tree. So you can see mid surface back supporting plates, and then when you expand that component, you can see the mid surface with its extracted thickness. When it doesn't have a thickness, you can assign one. So if it did miss, this is usually the case when the mid surfaces in one body has different thicknesses, so it struggles to extrapolate, but in that case, you can just go define any thickness that was relevant at the time. Taking it, I'll investigate that a bit later. Oh, it's just saying various. Okay, that's new. Okay, so it's actually capturing the various thicknesses of this body. Okay, then what I would like to do now is just kind of ensure that the mid surfaces that I've now kind of represent the 3D geometry and make sure that they are in contact as well. So you can do this by, I usually use the extend tool. So then it just highlights the areas that I can extend to a adjacent mid surface. Those are the ones I'd like to extend, and maybe some of those as well. These I don't think are necessary. Those are okay. Maybe this one is probably a tiny gap there. Okay, cool. Awesome. So the reason we want to kind of extend them is so we can share the topology over here. And we share topology in SpaceClaim typically for components that are bonded. So when you reduce the contact in mechanical, your model is also way more efficient. So it's always best to include as much shared topology as you can in SpaceClaim. So this is why we do it. I'm going to show you just how to do it now. I just want to maybe, while we do it, hide. Okay, cool. So if I go to the Workbench tab and hit share, SpaceClaim will identify all the topology that is coincident so that you can go share it. So if I click on these edges, the color code will change. So a red edge will indicate that it's free edge. I think a pink edge means it's got 2 connections, and a blue edge is 1. And then there's also a yellow one that's multiple. So you can use the color code to identify how many shared surfaces you have in a certain region. So in this case, I would like to share these 2 components. They're probably bonded. So to avoid having to use bonded contact in mechanical, I just share the topology over here. So I'm just do the same for this side, and perhaps for this plate over here. So this is a kind of plate-like structure that's just kind of connected through a, I don't know, joint to these plates, I guess, and then also connected to the port to the feet. So sometimes the mid-surfaces, if the thicknesses are similar, it will create one mid-surface. So if I triple click this, that actually highlights the whole body. But you can see here is a white edge. So these 2 surfaces are already shared. But if you see 2 surfaces that have a red edge between them, then it's probably necessary to share the topology between them. So let me just double check to see if I have any left. So these, for example, you can see this is actually the same body, but the mid surfaces were created separately. So I just want to ensure that I share these edges as well. Don't think it's necessary to share those. Let me double check. Yes, it is. Okay, so this will just share this edge with this top surface. So if you are confident that all of the faces and edges found by SpaceClaim need to be shared, you can also just click the check mark and it will share everything. But I like to kind of systematically work through everyone to make sure I'm actually sharing the right edges so that you don't make a mistake. You can also unshare everything again if you like to do that. So that's also possible. Okay, cool. So I have most of my mode surfaces ready now. And I think what I would like to do now is maybe extract my beam elements. And at the very end, we'll have to define some name selections for preparation for mechanical. So I just want to hide suppressed. So when I hide all the suppressed bodies, you can see that I have my solids that are still there. I have all my surface bodies, and all the associated solids with these surface bodies are also suppressed. Let me then just quickly do my beam elements at the bottom. I just want to take a sip of water quickly. So one of the coolest features that I really enjoy using is when you work with structures and you have a lot of like beams or channels on things like that, and you can't really model all of these beams with 3D elements. It's not feasible at all. Then you can use your beam elements. So the only thing that it requires is a constant cross-sectional area. So anything that has a constant cross-sectional area, you can actually extract a beam profile. You can also create your own beam profiles in SpaceClaim and define like the area moments of inertia values and things like that. but in this case, I'm just going to extract these beams over here. So as you can see, it's just converting the 3D solid into a beam. You'll also see your beams are listed in the structure tree with the extracted profiles, and all of the properties are captured in the component itself, and then it also captures the profile over there. Okay, so now just to make sure that my beams are also connected to my geometry, so you can bond things in mechanical, but as I said, I kind of prefer to rather share the topology. So I'm going to share this topology, but I think I need to. Yes, I need to extend them first. So let me just quickly extend these. So SpaceClaim automatically picks up to where it needs to extend. Cool. Okay, now that's ready. I'm going to just share this topology as well. So you can share edges with faces and vertices with faces and a whole bunch of different combinations. So let's just wait for SpaceClaim to quickly pick up. Cool. Okay, so it's found a lot of topology that we can share, but I'm not really interested in sharing all of those things. I kind of just want to share the beams here at the bottom. And maybe this one will also be beneficial.
Johnny, you just unmute quickly.
Did it just change to mute now?
Yes, we can hear you again.
Okay. Until which point did you guys hear me?
It was a couple seconds.
Okay. Well, maybe I hit something on my keyboard. Apologies for that. Okay, so I think what I just said was that, we can share our topology. You can share a variety of different topologies with each other. And again, this just kind of makes your life a bit easier within mechanical. Okay, so now we have this ready. And one of the last things that is probably necessary that I would like to show you and that makes your life a lot easier is to create some named selections. And this is just to make scoping of things a lot easier. So, for this case, I'd probably like to scope a mass or a remote mass or a weight or a force or whatever to these faces over here. So as I mentioned earlier, you can merge all of those faces as well, but I'm not going to demonstrate that as it takes quite a bit of time, but I will actually create a name selection for them. So to do that, you just kind of select all of the faces, then go to groups, and then you just click on create NS, which means create named selection. And I'm just going to call this remote mass surfaces. Okay, so now I have my group over there. So this just helps a lot in mechanical. So another thing that is very useful to create name selections for is your edges or maybe your washer faces where you have bolts. So as you can see, this geometry did not include bolts over here or screws or whatever they used to connect this, but I was going to represent it as beam elements or joints in any case. So in that case, when you in mechanical, and we'll cover this next week, you use something called the object generator, and this kind of just automates something repetitive. So in this case, it's not too many beams that we have to scope when we apply our bolts in mechanical, but in some cases you have, I don't know, let's say 100 bolts that you want to scope. So you can just use SpaceClaim to create the name selections and then use the object generator to automate all of that for you. So I'm just going to show you how we typically do that. So In this case, we're going to have quite a few beam connections. So I'm going to start with maybe the two 15 mil armrest plates. Okay, so let's start with these two beam connections here. You can see there are two plates and that are connected to this base cushion thing over here. So in mechanical, I probably need to scope a beam connection from this edge, or ideally you could also have a washer face that you imprinted to scope it to. So you can scope a face or an edge. In this case, I'm going to use an edge. So I'm going to start with the bottom edge there, but I'd also like to select this one. So you can use your power selection again to kind of hit equal to or smaller, same length. Okay, so it's all bodies. Okay, cool. So in this case, it's actually selecting quite a few. That's interesting. It's interesting to think that that edge has the same length as this one. But it's usually a bit easier to do that. But in this case, I'm going to create a name selection. Oh. Okay, no, let me just that. Select one. Groups, there we go. Cool. I'm just going to call this 15 millimeter armrest plates. So I'm just kind of representing the edges that are probably going to be scoped similarly. Okay, so I have those two together. Then I'll have, I'm going to select these two as well. This will probably be 15 millimeters. All of these now, but just want to demonstrate. And then we'll have probably the cushion. I'm going to just quickly hide these, it's a bit easier. And maybe this one. Okay, so here you can see how those plates will be fixed to the bottom. So in this case, I guess we could use this edge over there. Okay, maybe this one will work nicely if I use the power selection. Edges with the same length. Nope. Okay. All right. Usually the areas work a bit easier. So yeah, there are defined all the coincident faces or depression. Anyways, there are a variety of different power selection tools that you can try. It's quite fun to play with. Oopsie. Okay, it's just calculating something now. Still calculating. Sometimes this happens in SpaceClaim when you are in a tool and you accidentally select something and it starts calculating something. So that's just what happened. Okay. This will just be 15 millimeters base plate.
So these things I want to Unalibato straight 27.
Johnny, sorry, I just muted everyone there. Can you just unmute yourself again? Sorry about that.
No worries, thank you. Okay, cool. So I'm not going to go through all of these now, but essentially, what I wanted to show you is just that if you had a row of these kind of edges or a pattern of these two edges, like 100 of them in a row, then you can just kind of power select them and then create the name selection. And then in mechanical, next week, I'll show you how to use the object generator to actually automate that. So that's pretty cool. Okay, so this is our geometry that we have. I think this looks pretty good for simulation. So we have defined all our different kind of bodies, like we have our 3D bodies and our shell bodies and our beams. In the tree, you can also see exactly which surfaces have shared topology. So if you see an icon like this in the structure tree with a pink kind of edge, it shows that this will be shared. So when you do import into Workbench, which I'll just show you now quickly as well, just ensure that this property over here is actually share option. So there's also other options like none and group and things like that. So sometimes, I don't know, it kind of resets to the default. So I always just kind of double check if that's ready. Okay, so I'm just gonna hit save and then show you how to import the geometry into Workbench, but then that's probably where we will end for today. Then the next session, we'll take it from there. So we'll take it from the imported geometry and then start assigning material properties and our boundary conditions and so on. Okay, so this is our Workbench environment. I'm just going to drag a static structural onto the project page, and it's as easy as just right-clicking on the geometry. So you can also launch SpaceClaim from this environment, but in this case, just want to make sure I'm actually on my desktop. I'm going to open my Office chair. Cool. And then you see there's a green tick, which means it's imported successfully. And if I now open mechanical, it's just going to show you basically the same geometry that we just optimized for mechanical. So let's see. Cool. So it's now just going to import everything. Sometimes it takes a bit of time, fortunately. But if you look at your Workbench page and you see that it's, you can just look at the status bar to see what's happening. Okay. Okay, so it's just pre-processing some of the parts. Cool, it's almost done. Great. All right. Here we have our geometry in mechanical, and this is where I will be stopping today. Next week, we'll start looking at the mesh and the boundary conditions as well as the contact. So yeah, I hope there's some value that you can take from today's SpaceClaim session. Again, I didn't demonstrate all of the tools, but I hope I demonstrated some tools that will be useful to you as well. Okay, I'm gonna stop sharing my screen, and then now we have time for questions. Laura, I think.
Hello, thanks a lot, John Ray. I think that was very valuable to a lot of people. So a lot of the questions has been answered by Jessie during the session. So thanks for that, Jessie. Just to confirm, it is recorded. We will share the recording. It is also shared on YouTube. And as Jessie has been saying, you might find some interesting things there. If anybody do have a look on the Kiefersoft YouTube link. In addition to that, somebody asked about sharing the files. I'm sure we can, John Ray. Okay,
No, it's
so
not a
we'll
problem.
share the recording. We'll share the files so that you can practice. But just remember, this is a 3-session series. So at the end, we'll be providing you your evaluation license and the files so that you can use it then. Other than that, I'm just looking if there's any other questions. You can unmute yourself if there's any questions from the audience. But I think Jessie has been very good in answering all of them during the
Yes.
webinar.
He always is. Thanks, Jessie.
Okay, so there is a question.
Yes,
Tapelo is asked, yeah.
topology. I just wanted to find out what is the risk that one could find, maybe let's say missing areas of interest where there could be high stresses when we are making use of the mid surfaces. Because from how I'm seeing these mid surfaces being used, you must like have a quite bit of a background from mechanical to say if I'm doing a mid surface, I'm not actually missing, like for example, the chamfered phase. We know that those type of small areas, that's where sometimes the high stresses normally gets generated, or where you can have a skew mesh, which might end up leading you into the false result saying there is a high stress, whereas it's not a high stress. But I just wanted to find out what's the risk of actually making use of a mid surface.
Okay, so
Unfortunately, there's no one available at the moment. Anyone in
just
the
want to tell
office.
Jessie to mute himself quickly.
We are operating.
There you go. He's on mute now. Okay, cool. He was just answering the phone, it sounds like. So to answer that question, the use of mid-surfaces is mainly when you work with very large assemblies and you kind of want to capture the overall or the global behavior before you kind of start focusing on the details. So one thing that we'll actually be looking at in the last session of this webinar is submodeling. So in cases, like you mentioned, the mid-surface is not always adequate to capture the detail. In this case, you can build a submodel where you kind of zoom in on the area and you can actually do a shell to a solid submodel, and then you kind of just cut out that piece of the geometry, and then you can go and define all your detail, even though the rest of the model are shells, and you can include your chamfers and rounds and kind of zoom in on that area to get the resulting stresses in that case. So it takes a bit of engineering judgment to kind of decide where you can mid-surface and where not. But initially, when you have large models, I don't think it's feasible to do everything in 3D elements, because it will take so long to run that it will not be valuable anymore. Does that make sense?
Thank you very much. You answered me very well. I much appreciate it. Thank you.
No problem. Thank you.
Any further questions? No, I think that's it for then, John-Rie. Thanks a lot.
No
and
problem.
Thanks for everybody attending, giving us your lunch break on a Friday. So we'll meet again next Friday at 12 again, and we'll send the invites and all the information for the follow-up series.
Yes, cool.
Great. Thanks, John-Rie.
Thanks, Laura.
Cheers.